Hi, I am Sanjay Patel. Today, in this lecture, we are going to see some more examples of types of discontinuities. In the last lecture, we have introduced the concept of discontinuities of different types and solved one example. Let us recall, we know that if is not continuous at A, then there are two possibilities. So there are two types of discontinuities. One is known as discontinuity of the first kind, another is known as discontinuity of the second kind. So what is these definitions? Let us recall in short from this diagram. If f is a function from x to r and a is a point in the domain of the function, say f is a function from x to r and a belongs to the domain, if f of a plus or f of a minus or both does not exist, then f is said to have second kind of discontinuity. But when f of a plus and f of a minus both exist, then this can be further classified into two types. If f of a plus, f of a minus both exist and are equal, but they are not equal to f of a, value of the function, then it is called removable discontinuity. When f of a minus and f of a plus, they are not equal, then whatever the value of f is at the point A is not important. So when f of a minus and f of a plus are not equal, then function is said to have jump discontinuity. Further, I want to explain one more result which is useful in establishing discontinuity. It follows from a theorem which we have proved in our earlier lecture, and this result is given by this. Let f be a function from x to r and a belongs to x. Then prove that f is continuous. F is continuous at the point A if and only if for every sequence xn in x with xn converges to A, we must have f of xn converges to f of A. So this is the result which follows immediately from a theorem about limits of function. Just I will give you a hint for proving this. It is very simple. If you remember, we have proved this thing, that limit x tends to A, f of x is equal to L exists if and only if for all sequence or for every sequence xn in x with xn not equal to A, whenever xn converges to A implies f of xn converges to L. Okay, so just we have to put L is equal to f of A in this, and the theorem will be proved. This theorem will be proved because f is continuous at A. This statement means limit x tends to A, f of x is equal to f of A. So this is to be replaced by f of A, and with some other simple care you can prove this result. So I will be using this. So if you want to prove a function is continuous at A, you can simply take an arbitrary sequence xn with this condition xn converges to A, and you have to establish that f of xn converges to f of A. Or the other way, if you can find one sequence xn which is converging to A, but f of xn does not converge to f of A, Suppose if you want to prove discontinuity at a point, then just find at least one sequence which converges to A and show that f of xn does not converge to f of A. Then this implies f is not continuous at the point A. So this theorem is useful in proving discontinuity of the function. Okay. Let us start with examples. So let us take the second example. Let f be a function from R to R be defined as f of x is equal to 2x plus 3 if x is less than 1 and is equal to 3x minus 1 if x is greater than or equal to 1. And you want to discuss continuity or discontinuity of this function. Okay. So let me write only one thing. Discuss continuity of f and types of discontinuity if any means if it has any discontinuity, then also discuss the what type of discontinuity it has. So let us prove or try to understand this. So first of all, we'll draw the graph of this function to get an idea about this. Remember, for x less than 1, the function is 2x plus 3. Means on the left hand side of 1, the function is defined as 2x plus 3. And on the right hand side of 1, the function is defined as 3x minus 1. So both are straight lines. So if you don't take x equal to 1, then function is behaving nicely. It's a linear function and therefore it is continuous. So it is clear that the function f is continuous. The first thing is clearly f is continuous for every x belongs to r minus 1. So function is obviously continuous, can be proved very easily. So we are not discussing this in detail. Our main interest is to discuss different types of discontinuity if it exists. So let us consider the critical point. In such examples, we always concentrate more on the point of say difficulty or some critical point at which the function has some say problem, or you can say function is splitted into different formulas. So it may happen that the function curve may not be a continuous curve. For example, in this case, function is not defined with the same formula at 1. Okay, on left hand side of 1 it is 2x plus 3 and right hand side of 1 it is 3x minus 1. So for that, first of all, let me draw the graph. Just show you the graph of this function. This is the graph of this function. Say for 2x plus 3 it is a straight line, 3x minus 1 is also a straight line, and for x equal to 1, when x equal to 1, the value of the function is given by the second formula or second expression, that is 3x minus 1. So 3 into 1 minus 1, so 2. So when x equal to 1, function has the value 2 that you can see here. So this is the point at which the function has the value 2. Okay. And can take the function takes a jump, or it is breaking here at the point x equal to 1. So it is clearly not continuous at 1. But Also, we can see from the graph that function has a jump at the point 1, so it will have definitely jump discontinuity. Let us verify. So what I will do is I will find the left limit, right limit at the point 1. So I am taking what happens at x equal to 1. So f of 1 minus, that is left hand limit of the function at x equal to 1, is given by limit x tends to 1 minus f of x. That is equal to limit x tends to 1 minus, the formula of the function is 2x plus 3 when x is approaching to 1 from the left hand side. Because x tends to 1 minus means x remains less than 1 and approaching to 1. So one should use this formula. Now again, as we discussed earlier, the function is 2x plus 3, which is a continuous function, because 2x plus 3 is a linear polynomial. So I can directly substitute the value of left hand limit as the limit of the function, and it is nothing but the value of the function at 1. So simply it is given by 2 into 1 plus 3, so it is 5. So what I have proved is f of 1 minus is equal to 5. This is the left hand limit of the function. Okay. Now the right hand limit. For the right hand limit, let us consider limit x tends to 1 plus f of x. That means x remains greater than 1 and it is approaching to 1. So what is fx? Fx is given by 3x minus 1 when x is greater than 1 from our definition of the function. Again, 3x minus 1 is a linear function, therefore it is a continuous function at everywhere, at every point. So it is also continuous at 1. So I can put directly x equal to 1 in this because it is the value of the function at 1. So that is 3 minus 1 is equal to 2. So what we are getting here is f of 1 plus is equal to 2. So the right hand limit of the function at 1 at the point 1 is 2 and the left hand limit of the function at 1 is 5. So f of 1 minus is not equal to f of 1 plus, and therefore limit x tends to a, I can say f of x, limit x tends to 1 does not exist. Or let me write simply directly from the definition. Therefore f is not continuous. F is not continuous at the point x is equal to 1, and f has jump discontinuity. Jump discontinuity. Or you can also say f has first kind of discontinuity. First kind of discontinuity. Discontinuity at the point x is equal to 1. Okay, so this is our conclusion. The function is not continuous only at one point, and the type of the discontinuity is jump discontinuity, or you can say discontinuity of the first type. So let us solve the next problem, number 3. The function, let us take a function f from R to R be defined as f of x is equal to 0 if x belongs to Q, means x is a rational number and is equal to 1 if x is not in Q, means x is an irrational number. Okay. And we want to discuss the continuity or discontinuity of this function and its type. So discuss discontinuities of f and its type. Okay. So first of all, it is good to see the graph of this function. Remember, whenever x is a rational number, the value of the function is 0, and for irrational number, the value of the function is 1. So it seems that it is very badly discontinuous. You can see from the graph. This is a very simple graph. Okay. Oops. Let me select this way. Yes. You see the graph of this function. For rational numbers, which are shown here by dotted pink dots, there are infinitely many rational numbers here and infinitely many irrational numbers. So for rational numbers, the value of the function is 0. So y is equal to 0. And for irrational number, the value of the function is 1. So these green dots are the points corresponding to irrational numbers. So it seems that function is not continuous at all at any point. But how to prove this mathematically? So we get the idea from the graph that the function is not continuous. So let me prove in a general form for every point in the domain is R. So let us start with A belongs to R, be any fixed point in the domain of the function f, which is R actually. We have two possibilities for A. We can have either A is rational or A is irrational. So I can write A belongs to Q or A does not belong to Q. For each of this case, I will be proving that the function is not continuous at the point A. So let us proceed this way. Case 1. Suppose A belongs to Q. That is A is a rational number. So by definition of the function, f of A is equal to 0 because the function is defined this way. For rationals it is 0 and for irrationals it is 1. I want to show that the function is not continuous at the point A. Here f of A is well defined. So what I will be showing is limit x tends to f of x does not exist. For that, suppose if the function is continuous, then we know for every epsilon, if f is continuous, then for every epsilon there is some delta such that whenever mod of x minus a less than delta implies we must have fx minus f of a less than epsilon if the function is continuous. Okay, but I want to show that this condition is not true. So what I will do is, let me choose any delta and see what happens if I take the points satisfying that condition. So I am starting this way, you just understand. For any delta, whatever delta is given greater than 0, okay, for any delta if we consider mod of x minus a less than delta, mod of x minus a less than delta, that is a minus delta less than x less than a plus delta, or you can say x belongs to the open interval a minus delta comma a plus delta. All these are equivalent. For any x satisfying this condition, if we try to find mod of fx minus f of a, then what will we get is this. Here a is rational number and we know f of a is 0, so this is equal to f of x minus 0 because a belongs to q. So the value of the function is 0 and this is equal to mod of f of x. Now this x is any real number in between this a minus delta and a plus delta. So if I draw a number line here and explain, this is a, this is a minus delta and this is a plus delta. If I take any point between this a minus delta and a plus delta as x, any point here or here, so if I keep it fixed, you know there are infinitely many rational numbers and irrational numbers in any interval, whether it's open interval or closed interval. So this interval also contains infinitely many rationals and irrationals. I don't want to select rational number at this place. Suppose if I choose x, some irrational number between a minus delta and a plus delta, what I will get this is equal to 1 by definition of the function f. If x does not belong to q, that is x is irrational number and x belong to this is obvious. We are taking any x and it is keeping it fixed. Suppose x is some irrational number between a minus delta and a plus delta, then for that particular irrational number, the value of the function will be 1. Okay, and it is always possible, whatever delta is given, for every delta we will get some interval like this and it contains infinitely many rationals and irrationals. So this value is going to be 1 and obviously this one is not less than epsilon. I cannot make this fx minus f of a, which is going to be 1 under these circumstances, and I cannot make less than epsilon if my epsilon given is some value less than 1. Okay, so this discussion suggests for any given epsilon less than 1, you can take epsilon is equal to 1 by 4 or 1 by 3 or 1 by 2, anything, but less than 1, then you can, whatever delta you choose, then you can always choose one particular x which is irrational and you will get fx minus f of a is equal to 1, which is not going to be less than, it is not going to be less than your epsilon is equal to 1 by 2 or 1 by 3. So this suggests that therefore limit x tends to a, f of x does not exist. This does not exist. The definition of limit says for every epsilon there must exist some delta, but what we are showing here is if you take a particular epsilon less than 1, then for any delta greater than 0, that x minus a is less than delta is true, but fx minus f of a is not less than epsilon in all cases. So this limit does not exist, and this also tells something more, that left limit as well as right limit at the point a does not exist, because instead of taking the whole interval a minus delta to a plus delta, I can take only this much part a minus delta comma a and put it here. Then also I can explain in the same way that this limit does not exist. So in particular also I can say, in fact, it follows that f of a minus and f of a plus, here both limit, right limit and left limit does not exist. Does not exist. So what does it mean? That means f is discontinuous at a. F is discontinuous at the point a and the discontinuities of the second type, and f has second kind of discontinuity second kind of discontinuity at the point A. Remember, we have taken only one case, that A is a rational number, and we have proved that for any rational number A, the function is not continuous and the discontinuity is of the second type. The same way, we can discuss the case 2. Suppose A is an irrational number. A does not belong to Q. That is, A is an irrational number. Is an irrational number. Okay. Then by definition of the function, the value of the function at A is 1, because our function is fx equal to 0 when x belongs to Q and is equal to 1 if x does not belong to Q. So f of A is 1. Now here also I want to show that the limit at the point A does not exist. So whatever delta I choose for any delta greater than 0, if mod of x minus A less than delta, that is A minus delta less than x less than A plus delta is given, then if we consider f of x minus f of A, this difference, then what you will get is, since A is irrational number, f of x is 1. So I will get fx minus 1 because A is irrational, means A does not belong to Q. This now, here x is any point between A minus delta to A or A to A plus delta. So I can take anything I want. There are infinitely many rationals and irrationals. Again the same technique. So if I choose some rational number in place of x, then the value of f of x is 0. If I choose x to be some fixed rational number, if x belongs to Q, okay, it is fixed. It is some particular value or particular number between A minus delta and A plus delta. In this case, this value is going to be 1. So again I am getting mod of f of x minus f of A equals to 1, and obviously it is not less than epsilon if my epsilon given is some value, some number less than 1. So this discussion in the same manner suggests that if epsilon less than 1 is given, then whatever delta I choose, I can always find a sum x between A minus delta and A plus delta for which fx minus f of A is not less than that given epsilon. So again the same conclusion, that limit x tends to A, f of x does not exist. This limit does not exist. Okay, and not only that, in the same manner I can say the left limit and right limit also does not exist. Okay, so in fact, let me write. In fact, f of A minus and f of A plus does not exist. So left limit and right limit does not exist means the function has second kind of discontinuity. F has second kind of discontinuity at the point A. So what we have proved, whether you take rational or irrational, the function is discontinuous. So this is an example of a function. Remember, sometimes this kind of small functions or small example you must remember that, just let me write as a remark. So this is an example of a function which is this is an example of a function which is everywhere discontinuous, everywhere. Discontinuous everywhere. Okay. Let us take next more interesting problem. So we have seen that fx equal to 0 when x is rational and is equal to 1 if x is irrational is discontinuous or not continuous everywhere. Now let us take the fourth problem. The fourth problem is let f be a function from R to R be defined as fx is equal to say x if x is rational number, x if x belongs to Q and is equal to 0 if otherwise, means if x is irrational. So the function takes the value 0 when the argument is irrational. It takes the same value as x if x is rational. So discuss continuity and types of discontinuity for this function. So our question is discuss continuity and types of discontinuity. Types of discontinuity if possible. So let me take first of all some observation regarding the graph of this function. So function is a straight line y equal to x for all rational numbers, and it is again a fixed line y equal to 0, that is x-axis when x is irrational. So function's graph is again very simple. Let me show you the graph. You can also try yourself. Okay, so you observe here this function is as a graph which consisting of these two dotted lines. One is this x-axis, the green dots, and the line y equal to x, that is pink dots. This is for all rational numbers. This is if x is rational number, and this is if x is irrational number. Okay, and the function is again seems to be very highly discontinuous, but still it seems like all the points are concentrated. When you go near to 0, all the points are concentrated at 0. So at 0 there seems to be no break. From the graph we can have some intuition that there is no break at 0. All points are say merging in the origin. So we may think the function is continuous at A, and let us try what we get for the origin, that is 0. The function is continuous, but at elsewhere, means for all other numbers which are not 0, function is clearly seems to be not continuous. So we have to consider three cases. First I will consider the case corresponding to the point A equal to 0. So let us start with A belongs to R be given. It is any number in the domain. So I have three possibilities. I can take A is equal to 0, or A is a rational number, okay, but not equal to 0. So I can take A belongs to Q minus 0, or A is an irrational number. Basically there are two types of numbers, rationals and irrationals, but for rational again we further classify into two cases, A equal to 0 and A is not equal to 0. So there will be three cases we will be discussing here. So case 1, suppose A is equal to 0. Suppose A is equal to 0. What I will try to show here, as our discussion suggests, the function is continuous. So my aim is to prove, we shall prove that limit x tends to a, f of x is equal to f of a. Okay, but what is f of a? F of a is 0, because for a equal to 0 and 0 is a rational number, so fx is equal to x, so value of the function is 0. Now if I are given any epsilon, let me start with epsilon greater than 0 be given. What I want to do is I want to find some delta, so that whenever mod of x minus a is less than delta, mod of fx minus f of a is less than epsilon. Or let me write directly, because it is very simple. Or if you want to discuss separately, if you concentrate on fx minus f of 0 or simply 0, just think this way. If I want to make fx minus this limit less than epsilon, then I will get only mod of f of x. And mod of f of x has two possibilities. If x is rational, fx equal to x, so I will get mod x. And if x is irrational, I will get 0. So it is either mod x or 0. In any case, this will be less than delta. So if I want to make fx minus 0 less than epsilon, I must choose delta is equal to epsilon. So I get the idea from this discussion, and I will choose delta is equal to epsilon. Okay, then for any x with mod of x minus a less than delta, rather 0 less than mod of x minus less than delta, will get mod of f of x minus L, the limit is 0 here, is equal to mod of f of x. And this is equal to the same thing I am writing again. This is equal to mod of x if x is a rational number, and is equal to mod of 0, that is 0, if x is not a rational number. This is I am writing from the definition of the function f. But whatever the value is of fx minus 0, this mod of f of x minus 0, whatever the value we get, it is always going to be less than delta. Okay, because we have mod of x minus c here, a is equal to 0. We have a is equal to 0. So mod of x is less than delta, because mod of x is less than delta. So and by our choice of delta, I can take this is equal to epsilon. So thus, for every epsilon greater than 0, there exists delta is equal to epsilon, such that whenever mod of 0 less than mod of x minus a less than delta implies mod of fx minus 0 is less than epsilon. This thing is proved, and it means limit of the function at the point 0, I should write 0 here, because I am taking the point 0. Instead of writing a, I must write 0 here. So what is proved is limit x tends to 0 of f of x is equal to 0, but it is same as f of 0. So therefore, the final conclusion is f is continuous. F is continuous at the point 0. Yeah, fine. Let us consider the other two cases. Case 2, I am going to take x is say irrational number or rational number, anything. So case 2, suppose a belongs to Q and a is not equal to 0. So I am taking a as a non-zero rational number. A is a non-zero rational number. In this case, I will prove that the function is not continuous at a, because from the graph we have seen that there are a lot of breaks at all other non-zero numbers. So let us start by thinking this way. For any delta greater than 0 if mod of x minus a is less than delta. That is, again, a minus delta less than x less than a plus delta, then that implies fx minus f of a, this is equal to, I can write like this, f of x minus a. Why? Because the function's definition says fx is equal to x if x is rational number, and here we have taken a as a rational number not equal to 0. So we get this thing. Now this is equal to, now this x is here between a minus delta and a plus delta, and there are infinitely many rationals and irrationals as we discussed in the previous example. If I choose some irrational number in place of x, what I will get is 0 here by definition of the function. I must write if that x which lies between a minus delta and a plus delta is irrational number. If x is irrational, okay, that is x does not belong to Q. So what I am getting is mod of a as the final value of fx minus f of a. So for any delta greater than 0, whenever you choose any x between a minus delta and a plus delta, and if that x is irrational, we are going to get the difference as mod of a. And here with this mod of a is a positive real number, because as a is not equal to 0, I can say that mod of a is a positive real number. So this is not less than epsilon if I choose my epsilon to be a some number less than this constant. What is mod of a? It is some positive constant. So if I choose this epsilon value less than that constant, then I cannot make the difference of x minus f of a less than epsilon. So the same conclusion as in the previous case, in the previous example, that this means f of a minus and f of a plus both does not exist. Both does not exist, because even if you take a minus delta less than x less than a, then again for irrational number between a minus delta and a, we'll get the same situation. So f of a minus as well as f of a plus does not exist, and hence it says that f is not continuous at the point a, and which belongs to what? Q minus 0, yes, because it is a non-rational number, and the discontinuity is of the second kind. Okay. Now consider the last case number 3 for this example. Suppose a is an irrational number. There is no question of being 0. 0 is irrational. So a does not belong to Q. Again, from the graph we have seen that function is not continuous anywhere except at 0. So the same argument says for any delta greater than 0, if we have mod of x minus a less than delta, that is a minus delta less than x less than a plus delta, for any x, if we consider the difference mod of f of x minus f of a, then what we are going to get is this. Since a is irrational number and f of a is 0 for irrational, so this is fx minus 0 because a is irrational, and this is equal to mod of fx, which I can get as mod of x. Okay, I want to choose some particular value, x equal to x0 or say simply x. If I choose x belongs to Q, and I want to take x, that particular x, as a non-zero rational number. I can take a zero rational number also, but there are infinitely many rationals and irrational numbers between this a minus delta and a plus delta. So I want to choose some x which is rational number and it is not equal to 0, and that is possible. So I am taking a particular non-zero rational number, so I am going to get mod of x, and it is a positive constant, so it is not less than epsilon. It is not less than epsilon if my epsilon is less than that particular positive constant mod of x, for that number x belongs to q minus 0. So the same situation arises here, and we can have a similar conclusion that in this case also f of a minus and f of a plus does not exist. This does not exist. So again, function is not continuous at the point a belongs to r minus q. So f is not continuous, okay, at a which is not in q, that is it belongs to r minus q, means irrational number, and the discontinuity is of the second kind, Okay, so we have done this example, and what is the important thing about this example is it is a very interesting example of function which is continuous only at one point. If someone asks you, you can say this example. So I am just making a remark. This is an example of a function. This is an example of a function which is continuous, at only one point. So that is important. It is discontinuous elsewhere, but continuous only at 0. Okay. Let us go to the next interesting problem. So the next example, number 6, is this: let f from R to R be defined as fx is equal to bracket x. It is called bracket function. The meaning of this is the largest integer not greater than x. So this is very interesting example. Largest integer not greater than x. You know the meaning of bracket x. Say if I take x is equal to 1.5, then the bracket value of 1.5 is 1. If I take x is equal to 1.0001, then also the value of this bracket x is 1. If I take simply 1, then again it is 1. But if I take value of this as 0.98, then the bracket value of this is 0. But if I take negative value, say if I take minus 2.35, then the value of bracket x is not minus 2, it is minus 3. So what you have to think here is, on a straight line, what is the nearest integer on the left hand side of A? So if I draw line and okay. So on this line, you understand this way, for the last value, that is only the main thing. Say minus 3 is here, minus 2 is here, and minus 2.35 is somewhere here. Okay, so you have to think of the largest integer which is not greater than this number x. The number x is this minus 2.35 in this case. So there are many integers, say minus 3, minus 4, minus 5. All these integers are not greater than this minus 2.35. But out of all these integers, what is the largest one which is not greater than this? And it turns out to be minus 3. So this minus 3 is the largest integer which is not greater than this x. And therefore the bracket value of minus 2.35 is minus 3. So always take the nearmost integer on the left hand side of the given real number x. So that is the meaning. What will be the graph of this function? It will be an interesting exercise. You can draw the graph for different intervals of integers. So you can draw the graph between minus 2 and minus 1, then 0, 1, 2, like that. So always take this way. For example, if I choose my interval to be 1 to 2, means if I take these two consecutive integers, say n equal to 1, and the next is n plus 1 is equal to 2, then for any x between these two values n and n plus 1, what I will get, the bracket x is the nearest integer on the left hand side, that is the largest integer which is not greater than x, and that is my n in this case, so it will be 1. So for any number between 1 to 2, the bracket x is 1. If I take n equal to say 2, then 2 less than x less than 3. So for any x between 2 to 3, the bracket x is equal to 2, like that. So this way you can, for different intervals, plot the graph of this function, and you will get very nice graph which is known to you. And from that graph, you will see what is the another name for this. Yes, this is the graph of this bracket function, and it looks like steps. So it is also known as step function. It is also known as step function. So this is graph of fx is equal to bracket x. And from the graph immediately you can identify that the function has break at every integer. So from 0 to 1 it's a line segment, and then from 1 we have to take a jump and reach to this other part of the graph. Again we have a continuous part. Again we have to take a jump to get the next part. So function is taking jump at every integer. So function is not say continuous at all integers. So that is the first observation. And for all other numbers, for all other points in the domain, the function is continuous because it behaves like a straight line or line segment. So two observations from the graph. Function is, this bracket function is discontinuous at every integer, and secondly it is continuous at all other non-integer real numbers. Okay, so that part we are not going to prove, but let me take an arbitrary integer and discuss the continuity. So we'll get all ideas from that. So let me start with, let x be any integer. Suppose if I take x is equal to n belongs to z, be any fixed integer, any fixed integer. So we have on the number line, if I again consider if I consider a line like this and take two integers, say I want to discuss continuity of this function at the integer n. I don't know what is the value of n. And whenever we want to discuss continuity or discontinuity at integer, we have to always take a close region or a small neighborhood around this point. We don't have to think of all points on this number line R. Instead of, we should take some closed or small region, and that region I am going to take by taking two consecutive integers n minus 1 and n plus 1. So these are the two nearmost integers, the next integers to n. So I will be concentrating on this interval and points within these intervals. Okay, so if I define a function like this, so we have the function values, because now there are different parts, I have to write the different possibilities, because my x can be between n minus 1 and n, my x can be x is equal to n, or it can be between say n and n plus 1. So let me write here that x can be between n minus 1 and n, so n minus 1 less than x less than n, or it can be here n less than x less than n plus 1. So I will take three cases for defining this function at n. If n minus 1 less than x less than n, the value of bracket x, you know, fx is equal to, what is fx? Fx is bracket x. So value of bracket x will be simply n minus 1, the nearmost integer or the left or the largest integer which is not greater than this n or this x in this is n minus 1. And if the real number x is n, then bracket of n is n itself. But if x is between n and n plus 1, then the bracket of x, if x is anywhere here, then this n is the largest integer which is not greater than x. So again the value of function will be n in this case. So this your function is defined on a small interval around the fixed integer n. Okay. Why we have taken this way? Because it is easy to find now the limit of this function as x goes to n, because I want to discuss continuity of the function at the point n. So let me consider f of say n minus, that is left hand limit. That means limit x tends to n minus of fx. By the discussion, when x is tending to n from left hand side, when x goes to n minus, that is x remains less than n, the function is n minus 1. See, for all x less than n, fx is equal to n minus 1. So it is a constant function, n is fixed here, and this constant function's limit is n minus 1 itself. So what I have proved here is f of n minus is n minus 1. The left hand limit of the function at n minus 1 is n at the point n minus, at the point n is n minus 1. Sorry. Same way, consider f of n plus, that is the right hand limit of the function at the point n. So limit x tends to n plus of f of x is limit x tends to n plus. For the right hand side, we have this formula, that is n, the constant n, and being a constant function, the value of this limit is n itself. So what we are getting here is f of n plus is equal to n. So the right hand limit at the point n is simply n. So from these two observations, you can say immediately, okay, so let me write the conclusion, Thus, sorry. Thus, f of n minus is not equal to f of n plus. Okay. So therefore, f is not continuous. F is not continuous at n, at x is equal to n, which belongs to z. And since left and right limit are not equal, both exist, so it follows that f has jump discontinuity. Jump discontinuity at the point n, or you can also say that first kind of discontinuity. First kind of discontinuity at the point n. So a nice example, and again a similar example based on this bracket function is we are going to take as known as fractional part function. So we have solved 6 problems. Let me solve one more interesting one, the 7th problem. So the 7th problem is this: let f be a function from R to R be defined as fx is equal to x minus bracket x for every x belongs to R. So discuss discontinuities. Of f. First of all, here also, as in the previous example, we'll draw the graph of this function. Before that, you observe, suppose if we have, say, x is equal to 1.2, then the value of f of x is 1.2 minus bracket of 1.2. So you will get 1.2 minus 1, and that is equal to 0.2. So we get a fractional part of this real number. So it is also known as fractional part function. All values of this function lies between, say, 0 and 1. Let me show you the graph of this function. This is the graph of the function. All values of the function lies between these two limits, y equal to 0 and y is equal to 1. So the function consisting only of these pink lines, remember that. This yellow line and the other things are not part of the function. And function is, say, closed from this side, this lower part of this line segment, and open here. These are all line segments like this, closed here, and the line segment goes like this, and open at this place. Okay, so this kind of line segments are there. So it is something like tooth, say something like this. You can see it looks like a tooth which carpenter uses. It is also known as tooth wave function. Okay. And again from the graph, you will immediately understand that there is a break at every integer. Say at 1, second function goes from 0 to this point if you go this way, and at 1 we have a break. At 2 also we have a break. At every integer the function has a break. So from the graph it is clear function is not continuous at all integers as in the previous example. but it is continuous at all other points, because for remaining part the function is a line segment or a continuous curve. So here also I am taking a fixed point and discussing the discontinuity of the function at every integer. So let me start with an arbitrary integer. So let x is equal to n belongs to z be given. Okay, again to discuss the continuity, in other words to discuss the limit of the function at the integer, I will take a small neighborhood of this integer n. So I will take n minus 1 and n plus 1 as my, say, small region around this x. Okay, and define the function x minus bracket x again for this interval. So we can define the function f of x, which is equal to x minus bracket x, as there are three regions. Suppose x lies between open interval, in this open interval n minus 1 comma n, means if n minus 1 less than x less than n is given, then what can you say about this value? X is any point, we don't know what is x here, it can be any point between n minus 1 and n, but we can have the value of the bracket x. For any x between n minus 1 to n, the value of bracket x is n minus 1. The largest integer which is not greater than any x, which is here in this part, n minus 1 to n, is n minus 1. So in this case, the function value, this x is not, we don't know, so as it is, minus this will be n minus 1, because bracket x for any x here is always n minus 1. For x equal to n, if x is exactly equal to n, then this n, this is n, and this bracket n is also n. So I can write like this, n minus bracket n. So this value will be 0. Okay. And for the right hand side of n, means on this part, if you take any x, that is if n is less than x is less than n plus 1, then x minus bracket x will be, x we don't know, but bracket x we know, and it is n. For any x here, the bracket value is always this integer, it is the largest integer, not greater than this x. So we have this formula of x minus bracket x function on this interval. Now I can discuss very easily what is the left and right limit. So this is the main part. So therefore f of n minus, that is the left hand limit of the function at n, is given by limit x tends to n minus, what is the function formula for x less than n, because x tends to n minus means x is going near to n from left hand side. On the left hand side of n, the function is given by this expression x minus n minus 1. So I must write x minus n minus 1. Remember, this n is fixed, so n minus 1 is a constant. So x minus this constant is a simple linear function or a polynomial function, therefore it is continuous, and hence I can put the value of the limit directly, because the left limit and right limit both are equal and equal to the value of the function. So I can substitute to find this limit x equal to n directly, and what I will get is n minus 1. You understand why we are putting n here directly? Because this is a linear polynomial, it is continuous everywhere, so it is continuous at n also, and therefore its left limit and right limit and the value of the function all are equal. So finally we get n minus 1, which turns out to be plus 1, and gets cancelled. So the conclusion is the left limit at the point 1 is 1. Okay, and let us find the right limit now. Now f of n plus, that is limit x tends to n plus f of x is equal to limit x tends to n plus, x is tending to n from the right hand side, and on the right hand side of n the function formula is x minus n, simply x minus n. So this is equal to x minus n. Again, this is a linear polynomial and therefore its left limit and right limit is same as value of the function. So putting x equal to n, we get n minus n equal to 0. So what I have got is f of n plus equal to 0. So the right limit at n is 0 and the left limit at n is plus 1. So finally we have f of n minus is not equal to f of n plus, because the left limit is 1 and right limit is 0. So the conclusion is f is not continuous. F is not continuous at n belongs to z, and the discontinuity, since both the limits exist, discontinuity is of the first kind. Okay, and we can also say that, or it has jump discontinuity, since left and right limit are not equal, or jump discontinuity. Okay, so we have taken some interesting examples of different types of discontinuities of a function, and I hope that